Anybody feeling particularly overwhelmed yet? No? Good, good. University is all about time management. Comes in the semester, you've got exams and things to settle, assignments to give in. Week 9, week 10, classes go empty, students go crazy. They miss things, they can't do this, they can't do that, they find excuses for extensions. The time to start is week 1. Yeah? You don't fall behind, that's the main thing. Keep up to date. Stay with everything. You've got a schedule of the entire semester in front of you, all the assignments when they do, make a timetable, make a calendar, and follow that. Start things early. So you have this week's test with me to submit, but it's not very bad because you've had 1 or 2 of similar kinds of tests before. This is data that you will find in the final exam as well. So this is something you can play with. If you've done the last test, this is just a small extension on that. That's really all that's going on here. And then next, the final exam is again a bit more of an extension on the same, but a bit more data to involve, right? So all we're doing now is looking at Poisson regression. And so the only 2 major things we've done this semester is binomial regression and Poisson, that's all. 2 things, right? That's all. But there are some assumptions involved along there as well. And binomial can be different. Binomial can be essentially binary, where your observations are simply 1 or 0, or it can be actually binomial, which is not so often the case. You don't get binomial experiments so often. Mainly it's binary things you see more often. And then there's Poisson. The thing with Poisson is you have assumptions to satisfy it. The main assumption is that you require this dispersion thing to be equal to 1. That deals with the variance and how it behaves with the mean. Mean and variance are equal. If the variance becomes too big, then the data that you've got doesn't fit a Poisson distribution. And so you've got to look at some other options. The options we looked at so far are negative binomial. And then another one I've introduced, I think, in the exam, quasi-Poisson. Those 2. Quasi first, then negative binomial, in that order essentially. And you'll find usually one of those 2 will fit. If neither of them fit, you've got a problem with something else usually, and we saw that last week or a week ago, of these zero-inflated Poisson models, right, where you've got too many zeros so that it doesn't quite fit a Poisson distribution very well. And so we haven't covered it this year, I might cover it next year, but all you need to do is look up the stuff on Google and R and see how R fits it. What R does is it plants a binomial in the 0 place with a large probability of zeros, and then adds to that a Poisson distribution. So essentially, the model we have for the zero-inflated Poisson data is actually a mixture of 2. It's a mixture of a binomial, and on that is a Poisson. The binomial takes care of the extra zeros. The Poisson then takes care of the rest of it. Yeah, so this is a mixture model. It's a special kind of model. And mixture models are very important in many places because often you find data doesn't have, we expect sometimes, for example, data to be normal. It's not. It's actually a mixture of 2 normals. Maybe there's 2 or 3 normals on top of each other. It's like the thing you see with ANOVA, right? You've got ANOVA looking at the heights of men and women. You look at the data, the heights of men and women will be different, slightly different. If you plot them, it'll be almost sort of a bimodal distribution. And that's actually a mixture of 2 normal distributions. 2 together. So there's lots of stuff out there with data, many things we just don't cover. The hope is that if you go out there and learn enough about this stuff, you'll be able to pick out these things as you go, or you can ask somebody or learn some more statistics. You do a master's or PhD or something like that, get a bit ahead with the game. So again, repeating, the things we've done so far is binomial or binary and Poisson. Poisson, we've seen 3, well 2. We've seen the Poisson and negative binomial distribution, but also I'm introducing the quasi-Poisson in the exam. So quasi-Poisson again is one where if the assumptions aren't told, you can use it instead. So it's Poisson, quasi-Poisson, then negative binomial in that order. Try them. If you find that Poisson doesn't hold, you will know by the test that the dispersion is too large or whatever. Then you'll try one of the other ones as well, to see which one fits better. That's all there is. Now the rest of it is how you write it out. That's all there is. The analysis I expect for the next test this Friday, and for the exam will hardly take you a matter of well, maybe fooling with the data a little bit, mixing things around, half an hour or so, maybe an hour at the most, if you find some problems with how you're dealing with things. After that is how you write it up. So the data has been there early, and the test exam's been there early as well. Even if the test is Friday, this is week 10, you've got 2 weeks to do the exam. The analysis is not very hard. It's how you write it, right? I've got a paper, I think, out there on LMS as well for you to look at the kind of things, how you write papers, essentially. Because all the stuff you'll be writing, all you're doing out in your professional life is writing reports for others or reading others' reports and understanding what they're saying and criticizing it. Yeah. So the sooner you start writing stuff, the easier for you. Of course, when you get to third and fourth year, a lot of the stuff is writing. Writing is not as easy as you think. Quite often, most times, you write something and you read the thing, it makes perfect sense to you, but not to anybody else. So my supervisor, my ex-supervisor, if you like, kept saying all the time that as important is it to make sure that you understood, it's just as important to make sure you aren't misunderstood. Right? So read the thing both ways, carefully. Editing your own work's very hard. So submit something to me, as I think I've said somewhere. If you submit something for me to read, you must have read the thing and edited the thing yourself 3 times. It's a minimum, I think. 3 times. You pick up things as you go along. Now, the thing is, of course, after about 2 or 3 times, you start reading what you want to read, right? It says something else, you start reading something else. So start early, finish it, and put it away for a couple of days. Then come back and read the thing again. You'll find it looks different straight away, right? So this means starting early. A few years ago, when I was doing a first-year session, I put this in the final exam as a report for students in the 3 or 2 hour exam. Bang, here's the thing, write a report for me, this data. And they struggled. But they had practiced beforehand, and they won beforehand still. But they still struggle. Writing is not easy. So the past report so far have been 1 page. Now I've got more space. Explain things more carefully, put tables if you like, graphs if you like. There's still an appendix for our code and everything else, any other extra graphs you require. But write the thing following the structure I have put in there. Or if you think you have a better structure, use it, right? But I would advise don't deviate very much from it. You still require something like an abstract. Usually the last thing we write, introduction, you can put that together. Most of it will be doing with literature surveys, finding what others have said about this particular problem, putting it down there, and then your methodology of what you'll do with analysis, your results, and your you can go to conclusion or discussion and then conclusion. Discussion then conclusion, either way, or you can put the 2 together. There's a choice there. But you need to have those broad sections in there. Are there any questions? I don't want to do a lecture right to the end of the semester, so we'll have this lecture, and next week we might have a quick one, because this stuff is now getting mathematical, and if you don't have the right maths background, you haven't got a clue. But you can still do some things with it, and the major things you can do with it essentially is understanding what likelihood actually is, and how you can use at least R or some other package to find maximum likelihoods. Other than that, the rest of the stuff is mathematical. You'll need these for your 3rd year and 4th year courses, should you do those next year or so. So let's have a start with this and see how far we get today. I've got all the lecture notes online, and I'll release them in time. But what I will do, though, is go through this one today. This is week 10. And then next week, which is week 11, we'll do the entire lot and be done with it. So that means I won't cover everything. But you should, if you have the mathematics background, look at the things yourself beforehand. I'll cover the big bits that I think I want you to look at. And then we'll leave it at that, and maybe we'll meet in week 12 if you wish to look at the exam or questions related with it. So this is just essentially likelihood construction and visualizing, and then the rest of it in week 11 and 12 actually goes to actually working it out. So the idea here is that when you estimate parameters, there must be some methods for doing this. There are several methods. There's one called least squares estimate. There's likelihood. These are 2 big ones over here, and other methods basically depend on one of these ones here. And so what we're going to do here is, see, the things we've got so far from R and other places doesn't just happen automatically. There's lots of maths behind there. So what we need to do is work out things like how to actually estimate the parameters from for either models or for just particular distributions. And then also we need some idea of the sampling distributions, because when we have these, and that's what leads to hypothesis tests, and to confidence intervals, and essentially to inference. Without these sampling distributions, you can't do anything because you can't find p-values, you can't construct confidence intervals. So those are the kinds of things we require here. So first of all is how to actually find the estimates or estimators. What things estimate things. You'll find most of these actually work out to be reasonably intuitive as well. So we do require some idea of probabilities over here in distributions, and while we can do simple things like trying to work out the proportion or a mean for a Poisson, we can also use the same ideas for actually working out regression parameters as well, and that will be something we'll do later on next week or so. So the idea here is we look at this particular method called maximum likelihood estimators or estimates, and this really looks at just trying to maximize the probability. So nothing more serious here, and I hope you've read some of this stuff before. If you look at say simple experiments like tossing a coin or some simple thing like that, we want to work out the probability of heads, and so we can construct for ourselves some distribution if you like. So here I don't want to go through all the slides in detail. What we want here essentially is a probability of getting, say, the number of heads out of 10 tosses of a coin. And based on the probability, we can try and work out the value of pi, in this case, that maximizes the probability. And that's all this is. That's what maximum likelihood is all about. So this notation here really means nothing more than essentially what I'm after here is, I'm after the probability. Essentially, usually look at the thing is theta jointly with my data that I've got. With the observations, it's called O here, but I call them usually X as my vector of observations here. And so in the simple case of what I've got as the, I don't want to look at all this in detail. I want to look at, you can read this yourself, I want to look at the actual probability I'm getting here. So this is the example we're looking at here. This is, and another example related to this, success or failure of launching a vehicle in there. Here's a paper that this is based on, and you can look at this paper. Please, I advise you to read this stuff, because when you read this kind of stuff, you get the breadth of applications of statistics, how it is used, where it is used, and how people write these kinds of things. How do they explain what they're doing, and how do they explain the results in particular. So in this case, here are the 11 launches, and we've got success or failure for this. It's a simple binomial experiment in this case. Now, why is the number of successes here out of the 11 trials, M trials here? So why is binomial? We know that. And we have the probability mass function for binomial here. It is m choose y, pi to the y, and 1 minus pi, m to the y. Our interest here is in trying to estimate the pi. We want a value for pi. And that's what we're trying to estimate here from the data. Now, what we've done in the past is we've said, well, the best value we could find for pi is the sample proportion. So if you just go back for a second here, I've got 11, I've got 1, 2, 3. So I would expect my estimate of pi had to be 3 out of 11. That's what we have done in the past. The number of successes out of the number of trials. That's pi. That seems reasonable, and that's what we would intuitively try and estimate the thing as well. We want to see whether what we're doing over here gives you similar answers or something different, and if it's different, why is it different? So how do you proceed from here? Well, I've got the probability over here for this, and I can put the numbers in there if I wish. I've got 3 out of 11 so far. So certainly we know that here my pi is closer to 0.3 than to 0.8, for example. So what I can do over here is I can plot this. Here's some calculations to start off with. Working out probability of getting my 3 successes when pi is 0.3 comes to 0.25. If I take 0.8 as my probability of success, is quite tiny. So we can say this 0.3 is closer to the value of pi than 0.8 is. In fact, the ratio here, the odds ratio, if you like, in some way, not quite an odds ratio, but it's similar, is quite large. So it's very much more likely that 0.3 is a better estimate than 0.8. Now, here's the same thing, calculations from R, nothing more than that. So we know that D binomial gives you probabilities for single values. If I use P in this place, it will give me probabilities for being less than equal to. And if I use R, it gives me random observations or random simulations from those. And those are typical R commands here. So, well, at the moment, all we're using is non-technical words like more plausible, more probable, those kinds of things over here. But we can make it more precise, and that's the thing with mathematics. Here's a plot of the thing. If I take a look at a plot of the probability mass function, this one over here, with respect to pi, so I've got 11 trials, 3 successes, and decimal probability for 3 successes. And here's a plot of it. You'll find is actually very close to 0.3. In fact, of course, 3 on 11 is 0.333. So that's why it's close to, actually no, it's 0.303, isn't it? Recurring. So 0.3 is quite close to the actual value of pi, looking at the sample mean idea or sample proportion idea here. Okay, so what we can do is formalize the whole thing essentially is that the likelihood for discrete data, and is similar for continuous data essentially, is just the probability of the observations where we think of this now as a function of the parameter theta, because theta now is my unknown and I've got my probability here in terms of theta. And the thing with maximum likelihood is all it does is it maximizes the probability. So the likelihood I've got there, it maximizes that. That's what it does. That's the criteria we use for estimating the particular parameter. And so y is my data point, say in this case, and theta is my vector parameters. Usually there's more than one, but in our case it's simple. With binomial there's only one, with Poisson there's only one. If I look at regression, I've got more than one straight away, because the regression coefficients beaten out all the rest of it as well. So that becomes more than one in this case. So in this case I've only got one data point over here, one simple binomial probability model here. Now usually the likelihood is not a nice function to deal with, but its log is much easier. The log gives you something nice and simple, and so we deal mainly with the log likelihood. And so the way it works is I'm trying to maximize this function over here. And that's equivalent to maximizing the log of it. So I can maximize instead the log of theta, and that will be the same thing. And that's because log is an increasing function. Log increases. So if I maximize the function or its log, it makes no difference. They're equivalent in that case. And so as I was saying, we'll usually look at the log. Here's a plot of the function itself, probabilities, and the logs. You can see the logs flattens out quite a bit, because log is actually a very flat function. In fact, log looks like this. It's very flat indeed. It becomes flatter and flatter very fast. So that's why it flattens it out quite a bit more. As you go towards 0, you can see it goes towards, in this case it will start going towards negative infinity. As you go here, it will start flattening out and becoming closer and closer to the value over there as we go 0. So log of 1 is 0. So that's why it flattens out that way. But it still has a maximum in about the same place, in fact exactly the same place. So I can look at the log instead, and that's a far easier function to deal with. Now there is some issues here we can look at, but I just would like to look at the binomial to start off with again, and I'll get to the Poisson in a second. So for the binomial, which we had my probability for, in this case, the likelihood of theta, L theta here, given the data was, in this case it was m, and I had y observations that were successes, and I had pi to the y, and 1 minus pi to the m minus y. If I take a look at log of this, so the log likelihood in this case, the first thing is this number is just a constant. So I get some constant, which is the log of this thing, log of whatever this number is. It's just a number. M factorial or whatever else, it's a constant. I don't really care about it. It's a constant with respect to my parameter, which is in this case pi. So, and I should probably put a pi here instead of theta. So I'll just change that. Easy for me to do. So that first part's a constant. This here, next part is, that the log laws say that there's a few log laws that we need here. I've got log of a times b becomes log of a plus log of b. And the other property I need is that log of a to some power becomes r times the log of that. So I've got a product here, so this becomes plus over here. I get plus log of pi to the y. And I get finally also here plus log of 1 minus pi to the power m minus y. And if I use my second property here of logs, then this becomes still my constant remains, and I get the pi comes out, the y comes outside, I get y times log of pi. And I get m minus y times log of 1 minus pi. And now, is there anybody here to whom this makes no sense at all? Is there anybody here who has not done any calculus at all? You've all done some calculus. Good. So I can carry on in that case. So to maximize this function, I require to differentiate this and make it equal to 0. So I read L dash of pi here. Well, the constant disappears. And if I differentiate log, I get 1 upon pi. So I get y upon pi over here. And this here is m minus y over 1 minus pi. And the maximum occurs at what we call turning points or stationary points. That's where this is equal to 0. If I can solve the equation, I get the point where the maximum can occur. And I can check later on if the maximum actually occurs by a second derivative or whatever. So all I'm going to do is solve the equation. Well, that's not so bad. I split the whole thing apart, turn the thing upside down, and I can solve for pi from here. And if you do that, you will get very quickly that pi actually works out to be, no surprise, y over m. Number of successes over number of trials. Yeah, that's my maximum likelihood estimate. And usually you would add on the estimate to show it's an estimate over here. So I'll invite you to try and solve the equation yourself. It's not very hard. As I said, split the thing apart, you get negatives, turn the whole thing around, take all the pi's to one side, divide. You'll find it becomes essentially just y over m. So that's excellent. That's what we expect here. And that makes perfect sense. Now, a lot more needs to be done here. First of all, I have found the point which is possibly a maximum. I haven't shown actually it's a maximum at the moment. To show it's a maximum, it requires me to find the second derivative and see whether it's positive or negative, that kind of stuff. I won't do that over here. And the other thing is that when I have got my pi hat here, I still require to work out its variance and its distribution before I can do inference on it, in particular before I can find confidence intervals or hypothesis tests. And that all I can't just draw out of the air. Previously we looked at properties of this from somewhere else. I need to base it all on this likelihood principle. Within this framework of likelihood, I need to do all those calculations over here. And that can all be done here. So you'll find in the last lecture or so, you'll find calculations there. I won't even touch that because unless you have the maths background, you won't understand it. Those who have it, you can look through the whole thing and work it out yourself. Any problems, by all means, come and see me. But you need to see at least some of these ideas. So I'm hopeful for those who haven't done much maths at least, that at least you can get this concept of the likelihood, that all we're doing essentially is writing the probability of, it looks like probability of the data, and that's exactly what it is. But it's conditional on the value of the parameter, in this case pi. I'm assuming pi is known. In fact, pi isn't known, so I turn the thing around and think of this as a function of the pi instead, and I maximize that. And when I do that, I get my maximum likelihood estimate. Basically, that's the idea here. Now, if I repeat that with the Poisson, I can do a similar thing. You'll find I'll be able to work it out in a similar way. And so, for the Poisson, in this case, medical researcher knows there have been 3 cases of a particular disease in the past year. We're going to use a Poisson model for the data. Now, I've only got one observation here, 3 in the last year. So the only estimate I'll get ever out of this data is an average for the number of cases in a year would be 3. Yeah, I have nothing else to go by. one observation, pass on, then it must be the mean. If I've got more than one observation, if I've got some observation of the last 10 years for this disease, and I've got 3 1 year, 2 the second year, 4 the next year, and so on, then I can do something more with it. But at the moment, I've only got one observation. It's like I toss a coin once, if I toss a coin 10 times, and I do that only once, and I get 7 heads, my estimate for the probability of heads is 7/10. If I repeat that several times, I've got several observations on this binomial 10 distribution, 7 here, 5 there, 4 there, and so on. I've got more data, I can do more with it. In this case, I've only got one observation. I'm only ever going to get out of it. However you try and work it out using maximum likelihood or whatever else, you should get nothing more here than my lambda hat, or my estimate is just 3. And that's what you'll get out of this. Anyway, we'll get to that later, I'm sure. So all this is doing is taking a look and saying, all right, in this case, I want to think of this as a function of my lambda as my unknown. And so my lambda occurs in the top line, and the bottom line is just a number. And so if I ignore the number, it doesn't change my maxima in any way, right? I'm just dividing by a constant in this case. And all we're doing is plotting the two of them together with and without the 3 factorial. And you find that it doesn't change much at all. It looks the same shape. It's centered around the same area as you expect. All we're doing is scaling the thing. So that makes perfect sense. So whether include this constant over here of 3 factorial on the bottom makes no difference to the maximum likelihood process, and neither to the actual answer we're going to get in the end. So here is the log of that function there, and the constant of course comes from log of 3 factorial, which is just a constant. And so I get here from here log of e to the negative pi, where log and e are what we call inverse functions. From there I get just negative lambda over here, and this lambda cubed becomes 3 log of lambda, and I get this expression here. Now if I was to differentiate this, so I get L dashed at lambda. Well, the lambda, negative lambda gives me simply negative 1 over here, and this 3 log lambda gives me plus 3 on lambda. And you can see clearly if I solve the equation, I get my best estimate from this is going to be lambda equals 3. Very easy indeed. Simple. But as I say again, we need to do further work from here to find the variance of this estimator and all the rest of it to go to inference. So this is the same, including the constant or not including the constant makes no difference at all. So what you'll find here is this is the calculation for that. You can repeat this particular code yourself. So this is the calculation for the local likelihood with the constant 3 factorial on the bottom here, and this is the same code but without this extra factorial of 3 factorial over there, and this is the log likelihood we're looking at. All it does is it changes the thing by that factor, and you've got the plots over there from before and the same kind of plots over here. So the same value of lambda maximizes in each case, whether you include or not include the 3 factorial, but you'll find of course that the values will change in the same whether you take the log or the actual function itself. All that will happen is the scale will change here, but the graph looks exactly the same with the log, without the log, with the constant, without the constant. And so all we're trying to do here is hand wave and justify that, okay, it doesn't make a difference whether they include the constant or not. So generally speaking here, if I've got more than one observation here, y1, y2, y3 on the same distribution, then all I'm doing is looking at the probability, the joint probability of the y's here. Now, of course, the one big thing we'll do is we'll assume they're independent. And independence allows me to actually break this probability into a product of probabilities. So that's what this is all about. We say that random variables y1 to yn are independent if the joint probability is just probability for each of those individually, then multiplied out together. So independence is a very nice and simplifying assumption here, simplifying property. And of course, you try and make sure the data you collect is independent. There are situations where you don't get independence of data, and that's a problem altogether. So if that's the case, we can just factorize everything out. So far we looked at single observations, Now we're looking at more than one observation. And so all that happens is we're just simply going to multiply everything out. We know how it works essentially. If I've got a product of C times some AI here, then the C will be multiplied n times in this product. It can come out as C to the n. If I've got A times B in this product here, I can break it into two products. So those kinds of things work out here without problems. So here, of course, it's clear it's going to be CA1 times CA2 times CA3 and so on up till CAN. And I can take all the C's outside and I get my result. The same with A's and B's here. I get A1, B1, then A2, B2, and so on. I can put all the A's together, all the B's together. This becomes two products separately. And so those properties will hold. But for our case, are we interested in the likelihood idea here? So now I've got likelihood of a vector of observations, or more than one observation. And by this idea of independence, all I need to do is work out the probability for one of those, and the other ones are all similar because it's from the same distribution. Multiply the whole thing out, and then I have my likelihood. Nothing much changes here in the process. All I do is, because I've got more data, then my estimates are going to be better. The equations are slightly different in how I solve them. Nothing much changes. Poisson case here, if I've got data from y1 to yn which are Poisson distributed, then what I need to do is, the likelihood here is, the likelihood of each one of those is e to the negative lambda, lambda to the yi over yi factorial. Now you can see here, the e to the negative lambda is my constant term. It doesn't depend on my I, which is my index of multiplication. So this comes outside as e to the negative lambda to the power n. Now we know that if it's a power of a power, multiply the powers out together. So I've got a to the n to the m. This becomes a to the nm. And so that's what's happened here. I've got e to the negative lambda to the n becomes e to the negative lambda n. And then these other products over here break apart. The constant doesn't matter. I know that because this will disappear when I take a look at logs or whatever else. So I've got essentially e to the negative lambda n, and I've got lambda to the yi. Now, we know that the products, as far as products are concerned here, this one simply becomes lambda to the y1 plus y2 all the way to the yn. And here's the sum of the yi's. You can see if I just divide this by n and multiply by n here, so the trick I'm sure you've seen before somewhere. I just multiply this by n and divide by n. So this part is actually y bar. So this becomes ny bar. And so I've replaced this by ny bar. And there it is, lambda to the ny bar. And the rest is a constant I can just ignore in time. And I'm saying essentially this likelihood is proportional to this without the constant. And so I've got a simple likelihood here in this case. My likelihood for lambda is e to the negative n lambda and lambda to the ny bar. Now, if I take a log of that, if I take a look at the log of that, yeah, then you can see what happens. I'm taking a log of just e to the negative lambda. Yeah, so what's happened here is, by looking at the log of the product, we're just summing the things in the product itself. So the log of a product becomes the sum of the logs. So it's log of each of those individually, and this is negative lambda, all the rest of it. You find this becomes still the same, because this negative lambda over here, when I add n times, it becomes n lambda over here with negative. This yi log I plus c, and again the same thing. The log is a constant, and the sum of the yi's is just n y bar. And so essentially what I'm saying over here by this kind of expression is, if I replace every value of the data by the average, the sum is the same. That makes perfect sense. That's what the average is all about, right? So I'm saying yi, sum of yi is ny bar is summing y by n times. If I replace every data point by the average, then I get the sum of those two will be the same. So this is my log of the likelihood, and if I try and maximize that, I will be differentiating this. So if I take a look at L dash in this case here for my lambda, from the first expression we get just negative n, and the next one I'm going to get here plus n y bar. The function is in terms of lambda. I get upon lambda over here. The constant disappears. I get 0. If you solve this equation, first of all, the n's cancel off. And you can see what I'm going to get from here is that lambda hat, my best estimate here, is simply y bar. So that makes sense. The mean of the Poisson process is simply the mean of the data. Makes perfect sense. But again, as I said before, to be able to do the whole construction of the variance and distribution, all the rest of it requires me to calculate things and work still within the likelihood framework. So that's how simple this is if you understand the calculus. Nothing much more than that. Now later we'll find that this thing here, the derivative, is called the score function. And that has particular properties we'll need. And so that the second derivative also has particular properties. And essentially, in some way, it scores the value of lambda as being how likely it is, how far from the maximum it is. Binary data, similar things. Again, we'll have here the Bernoulli distribution in this case, and I can look at either the thing is Bernoulli or binomial, makes no difference. And in this case, we can still write down a likelihood, log likelihood, and we can still work out the maximum likelihood. Of course, if we have 6 wins out of 10 games, then the best estimate for my pi would be still as before. We'd expect pi hat to be 6/10 in this case if I use it, if I calculate the thing by my maximum likelihood. Okay, so here's our output for the calculations. All we're doing is looking at the graphs of these things by looking at the thing is a binomial model or a Bernoulli model in this case here. All the changes here is that just the shift of the scale in the y-axis because of some constants involved in the Bernoulli versus binomial. That's what is going on here. Bernoulli doesn't have the binomial particular coefficient that we get from the n choose y bit, because Bernoulli is just a product of the probabilities itself, independence, and we've got the whole thing there. So it works out to be exactly the same, except the Bernoulli model actually misses the constants. The binomial has the constants, so all we're having is a shift in scale in the y-axis. Otherwise, you can treat the data as Bernoulli or binomial. You've got no difference at all in this case here. The last example we look at here is this from the Apollo 16 mission. They had 62 centimeter core of soil from the landing site, and this soil is classified as coated or uncoated after they examined it for coating with dust and glass fragments. So this is grains of the lunar soil, and so the data here essentially is either depends on the depth, the top or the below, and the number of grains sampled here and the number that are coated here in each of those. So the idea here is, from geology, the coat index will decrease with depth. As you go deeper, the coat index decreases. So at the top, you expect to have a higher coat index, which means essentially the ratio here, 64 to 84, will be higher than the other one here as a proportion. So we can think of this as a proportion in this case. So y1 is binomial, the number in the first, and y2 is binomial, the number in the second. M1, M2 are the number of trials. Pi1, pi2 are the two probabilities over here. How would you find the probabilities here, pi1, pi2? Well, you've got a joint distribution here, assuming independence, the same idea. Take one binomial, another binomial, multiply them out. So you've got the first one here is binomial with m1 and pi1 as the probability. And the second is binomial m2 number of trials, and pi2 is probability of success in this case. And the joint distribution is exactly the same as just multiplying those together. You still get this constants out here of this product over here, but then you've got the usual Bernoulli construct of the number of trials, successes, and everything else. So 64 in the first one successes, 20 failures, and the other one 35 and 38 with the appropriate probabilities there. So nothing changes. I can just take a look at this. The only problem is I've got two variables here, not just one variable. So to do this properly using calculus requires me to use multivariate calculus over here. If I take a look at the log of this, the constant disappears, and the thing with the log is you can see the big advantage is these things are powers of pi and everything. Log makes it more linear. It gets rid of powers, and I've got logs to play with as well. Only if I look at the derivatives, everything becomes clear. Here's the log likelihood. So the constant is just at the end here, and I've got the logs of the appropriate bits over here. So for those who have done the higher maths as well here, I require derivatives of each of those with respect to each of those pi 1 and pi 2. It doesn't look very difficult actually. All I want here is what's called a partial derivative. First of all, with respect to pi 1. So when I do this, all I'm doing is I'm holding pi 2 constant. So I'm saying pi 2 is constant. In other words, no derivatives with respect to pi 2 appear here. And from here, I'm going to get my first equation is going to be 64 over pi 1. And I get plus, actually it's minus, because the minus in the bracket over there. So I get minus 20 over 1 minus pi 1. And similarly, the other equation, and to actually maximize this, I want to solve this equals 0. And my other equation is going to be with respect to pi 2, I differentiate this with respect to pi 2, so I'm going to get here the same kind of expression. So it's 35 on pi 2. This again minus 38 over 1 minus pi 2. And I want that to be equal to 0. So in the end, it's essentially, I've got the likelihood equations, if you like, for the pi 1 and the pi 2 separately. Nothing very unusual about that. And that reminds me, I think for the first example, I did miss a minus sign there in that case. When I differentiated that, was that a miss of me? Back over here, yes, there's a minus sign there. All right, so barring that, everything else is okay. So you can see that here nothing much changes and nothing is surprising. I get the equations for pi 1 and pi 2 separately, which means this is the same as actually estimating for pi 1 first and pi 2 separately for pi 2. It works out fine here. In general, of course, you don't expect this kind of luck to hold for you. So often the derivative of a function here, as I've got here, for one parameter will involve the other parameter as well. So I'm going to get, in this case, I'm going to get simultaneous equations to solve. And usually those equations are non-linear, which means I can't solve them by hand. I don't get closed expressions for these kinds of things very often. Sometimes we're lucky, otherwise it doesn't work, which means I must solve those equations numerically. So often, most often, the maximum likelihood equations are solved numerically by using something like R or some other package, and it gives you some estimates over there. The other thing is there's no guarantee you're going to get maximum likelihood in the first place, because it depends on, you've got here what's called a wire plot or perspective plot of what things look like. In this case, we're lucky there's only one peak for the thing. But often we aren't so lucky because even simple functions might have more than one peak here. If I'm trying to maximize this numerically, what happens is my numerical methods are so that it tries to use usually what's called gradient methods. So by gradient methods, we find the sharpest increase and we get there, now it's decreasing, so we get stuck here. We start somewhere here, we might get stuck here. So where we end up often depends where you start off with, right? You need to start somewhere. And most algorithms will choose a starting point or invite you to put a starting point in there. You might have a good idea of where you want to be. So you might say, I'm going to be closer to here somewhere, so I'll choose my starting point to be here, which means you probably will end up there if you're lucky. But it depends how this other part here looks, because it might actually slide this way and end up here somewhere instead. So these are quite tricky things to look at in general, but luckily mostly it works out nicely for us in the cases we look at. So here you can see it's a nice, as a function of pi 1 and pi 2 separately, I draw the function here in 3 dimensions. I've got a nice little peak there. That's the wireframe plot, and here is the log likelihood of that thing. Again, you get similar things. So it sort of is much flatter because of the log part, but it's still there's a maximum there somewhere you can pick out as being in that particular graph. So with 2 parameters, it gets more complicated. As you can imagine, with 3 or 4, it gets messier and messier, and often, of course, you can't plot these things so nicely. Here is the log likelihood for the particular plots that you've got there, and calculations for the log likelihood here. Now, so nothing too much more than the R code here. So basically, the idea here with the summary is that we're looking for this idea of maximum likelihood, which means essentially we find the probability of the data together with the parameter we're looking at here, and we can maximize that by essentially looking at calculus, and we can find the value by essentially solving the equations, and we get the answers from there. If you don't like calculus, haven't done calculus, this will be a mystery to you, but essentially the only thing you need to understand is there's a method behind this that actually works. And next week we'll take a look at trying to maximize the likelihood of these kinds just through R. The more interesting problems are trying to look at regression models and trying to find MLEs, maximum likelihood estimates, of the regression parameters. That's a much more interesting problem. We'll look at that for the Poisson next week, but I don't want to spend too much time on that because, as I say, that's not the most interesting things for us in this course, I think. But the thing is, you'll need this for your higher courses, the third year and fourth year courses, so at least you've seen what a likelihood actually is. Nothing more than writing the probability of the data down, and that's all, taking logs if you can. Any questions so far? Who hasn't done this kind of calculus over here? Who hasn't done that? Okay. So you haven't done maths 10, 11, 10, 12, you won't see that. But if you've done, say, something like 1721 or 22, you will have seen the symbol derivative. All this is a different symbol, but the same idea. When I have pi 1 there, I differentiate with respect to pi 1 and hold everything else constant. So pi 2 is a constant as far as I'm concerned in this part. When I get to this part here, my derivative is with respect to pi 2, so I'm holding pi 1 constant. Yeah? It works out in exactly the same way otherwise. So there's a bit more here to be done. In particular, sometimes for 2 variable things, you don't get a maximum, you see, because you might have what's called a saddle point. I don't know the details of that, but sometimes you get problems with that. I'll stop there. If there are no questions with this, that's fine. If you have questions, please do ask. But yeah. Lab test 5, no, because there's one person not submitting till Friday. Extensions because of other issues. My idea would have been to have those tests and solutions posted straight after they're due, so you can look at the solutions. But I can't put them up till Friday because there's one person still to do it. 4 is up there, isn't it? Yes, absolutely. It's probably on the LMS. I haven't got a copy of my disk over here. So lab test 4. Download this. This is an old version. I thought I had done a better one than this one. I think I changed something. I changed this particular output there. So Now, you would have known that this data was available, well, this paper was available online, so I would hope you read the paper, because that tells you at least how we wrote the stuff out ourselves, or the focus was here. So the basic idea for the first part was look at the performance of students according to whether they attended this support program or not. And so this is the basic introduction, what's happening here. Nothing more than just that, not much you can write in a page of a report, but if it's a journal article, you'll probably expand, I think, to 500 odd words or so. So all we've said is basically what's going on here. We've got a support learning tutorial program over here, and we're looking at the analysis of the data on this program to determine if the effect of SLT on student performance. Methodology here, exactly what we had. We had data in two files. First was aggregates, which we had to expand out. Excuse me. And this was just a matter of whether the students had attended SLT or not, and so this was whether they had actually had more than 5 or not. And the response was just binary in this case, failure of passing. The second file contains demographics. So in the paper you have found that we didn't have demographics. In here we did have demographics. In the paper, I think, I'm not sure whether it was written down there, one of the issues is that, of course, demographics helps moderate for differences between students, which you can't see otherwise. So maybe the students who went to SLT were different demographically than those who didn't, and so that adjusts for that. So it may be the students who went to the SLT sessions came from poor backgrounds, mathematically speaking, and those who didn't go didn't need that particular support. So if you find differences between students' performances and those who went to SLT perform worse, it may be because they were worse to start off with. But you see the background and the demographics adjust for that difference. If you don't have that moderation, you can't really compare the SLT without the SLT. It doesn't make any sense, right? That's why at least here you've got the right data. You have got demographics over here, the students' ATA, all those kind of things make a difference over here. And so that's all this describes here. We had data in two files, what the first file contained, what the second file contained over here, and that we had to merge them together with the demographic data. We put a binary model in there. Results here, summaries. So no unusual records over here were observed. The distribution of ATA scores were similar for both passing and failing, which is great to see. It's not atypical. Some students with high ATA end up failing because they think I got the thing, that they don't work hard enough. The model over here for the binary log model, main findings were just these here. So I've got the description of all the other bits and pieces first, the effect of all the other, like repeat students, the students in 2013, and by year or cohort, repeat students who came to SLT. This is for the interaction term. Otherwise, those who came to attend SLT had passed rate of 1.6 times. And the most important thing here was this one over here, linked with this one there, because that is what ties in with attendance at SLT. Excuse me. So overall, saying that repeat students do better if they come to SLT, but otherwise, for every student who comes to SLT, the chance of passing is a lot higher. And then it turns out that the odds of passing for male students in semester 2 was 1.2 times that for the female students in semester 2. Again, this is an interaction term. So you can see all the stats has been hidden behind there. I don't even know whether they mentioned the word interaction somewhere there. Yep, I did, which is good. So those are the interaction terms. I didn't actually mention interaction specifically in the output in the results section or in the discussion session. We put in just the important bits here, explaining what actually happened without using technical terms. Now I've got a bit more here than you might normally. I could write this whole thing and save space in this part at least by, instead of putting dot points here, but making them shorter and paragraphs. So that's why my report's a bit longer, but I wanted to put more in there so you could see the kinds of things we're writing here. So here's the discussion conclusion. The year-based, the important things. I haven't got everything in there. The idea of the SLT, and the repeat students over there, and then the thing with the weaknesses in the model over here. All we have is, we had a broad idea of those who came to more than 5 were classed as yes, and those who came to less were classed as no. That's very broad indeed. It may be what we want also instead is to see how many they came to. So we should know exactly how many they came to. Yeah, the number of sessions attended. Also, what topics were covered. So if I know that, for example, I covered algebra in one particular session, in session 2 say, and I covered logs in session 3, I can then take a look at the exam, and I can take a look at the marks in algebra for the SLT and the non-SLT students, and the same in the logs, the exam marks in the SLT and the non-SLT crowd. I can do a lot more with this, is my point here. So there are ways of improving this particular whole idea, not just by seeing whether it's a yes or no for attending or not attending, working out how many they came to, what they came to, and how they scored in the things they came to. You can see I get much more finer detail there, and I can improve it many ways, many particular ways here. Is that good enough? Yep. R code. Here's the data. We've done this expansion before. You probably will find, I think there's an R package that does it as well. So here I did the thing individually, but you'll find some R package does the thing as well. If you just look it up on Google, you'll find the thing. Looking at aggregate data. Summaries over here. So this is the second data set I've read there. Now the assumption here is that once I've unmerged the first one, and I merge these two together, once I've done for the first one, I've actually made the thing as individual records. When I merge this together, all the records line up. Yeah, and that will be the case in this. This is the assumption here. So here is the full data set in that case when I've merged them together. So I put those two together, powerful and this power is data frame. And year is a factor, and age in this case also is a factor, because you see age, if you look at it, you might be missing the output here, but age doesn't have too many levels here. And only a handful of levels. Looking at first year students, maybe 17 to 21 or something. You might find some people a little older, but otherwise it's nice to have that as a factor. The other things is, you see, look at year and semester. So these have been combined to form this thing called cohort. You look at cohort as a variable by itself, or you can look at year and semester separately. Either way works. You might look at year and semester as interaction term. That also works, but that doesn't give you anything much more than the idea of cohort. Yeah. So the R codes here, and I've got lots of interaction terms here, right? And somebody questioned me because in the next test, which was 5, I said, don't put too many in there. Now, yeah, I'm putting quite a bit in here, but I'm exploring at this stage, you see. So my interaction terms of here, this is an exploration to see what actually the behavior of the thing is. You'll find, of course, by the end of it, I've only got a few available here. Now, the important thing is you can't put too many interactions in many cases because of how much data you have. Interactions suck up lots of what we call degrees of freedom, right? If you've got something like 30 observations, and I put in 10 interactions, each of the interactions will take out some of the degrees of freedom. I need some left over. In other words, if I'm trying to estimate in a data set of size 30 something like 25 parameters, it doesn't leave me much of a, it almost says everything if you like. So if I've got, say, 1, 2, 3 points, I can always put a quadratic through those. I can always, if I model the thing as a square, a quadratic term, quadratic function, I'll have a perfect fit over there, right? That's the problem. In other words, I'm overfitting in many cases with data. So here, this is probably not the best fit. I'd probably have overfits over here, but I'm exploring this to see what's going on here. And my first, someone explains to me. Now, the point is, you'll understand with some experience and practice as to what kinds of interactions you really want to look for. So I put everything in there just to see the behavior to start off with. But I know I can handle any problems that arise from there. So often you'll find when you fit interactions, you get in the output things like NA terms. Yeah, you might find some NA terms like this one here. What it tells me is that if I look at 2018 semester 2, one of two things is happening. See, I've got year here. I've also got semester here. Yeah? And I've got the direction terms as well here. So one or two things happens. Either you've got some variables that actually align exactly, and so what you're trying to estimate by this particular variable has been covered by the other one already. In that case, they won't both be in the output here. One will be NAs. Or I've got nobody in semester 2, 2018. There's no interaction. So if I've got something like, for example, I take a look at a disease. That's, well, easy. I've got males, females over here, and I've got, say, diabetes. Now I've got 20, and I've got 10 here, males, females with diabetes, and now I've got here I've got 30 and 0. So there are no females who don't have diabetes. So in the direction term here won't work because I haven't got all levels of males and females available for all levels of diabetes. Yeah, some missing links, some missing entries there. So in other words, my interaction terms just won't work there. And so that's what you're finding if you're fitting too many interaction terms. Some of them just don't have what we call crossed levels. If I look at this as data, if I've got, say, male here and female, which is the opposite of male, if you like, and I've got diabetes, yes or no. So male is going to be, well, let's call it gender in that case. So it's going to be male, and I'm going to have diabetes, yes, and I'll have that occurring 20 times, right? If I look at male and diabetes now, I'll have that in the record a total of 30 times. If you look at female with diabetes, yes, I'll get 10 records, but female with diabetes, no, there's nothing, doesn't exist. So they aren't crossed, right? There's not a full set of observations available for all levels of male, female together. So you'll get NAs there in that case. So that's another problem you find with the data of this kind. But I've got lots of interactions there just to fool with the data to see what it looks like. That's what I'm doing over here. But look at my next model. It's thrown up. It actually reduced quite a bit already. I've taken quite a few interactions out because, by looking at this, I know the thing you take out in the model to start off with. If you've got interaction terms in the model that aren't significant, take them out first before taking main effects, right? Take them out unless there's a reason to keep them, and the reason will be context-based. I want the interaction here to work. I need to look at the interaction more carefully. So you'll keep that on for a bit longer, and then throw the other terms out. But otherwise, interactions are the first thing you throw out for two reasons. One is, if I've got like this one here, males, females, this is two variables, but altogether 1, 2, 3 terms will be fitted to that. Actually, two terms will be fitted, right? I've got altogether 2 variables to be associated with that and 2 particular coefficients to be estimated. So there's more coefficients with interactions, especially if you've got interactions with many levels in there. Altogether, if I've got here with males, I've got 2 levels, so these 2 minus 1 terms over here. Diabetes 2 levels, 2 minus 1 terms, altogether 2 minus 1 terms, 2 minus 1 term over here that comes out of it. If I've got something like, say, 4 levels of one variable and another, say, 5 levels of the other one, I'm going to get 3 times 4 equals 12 variables to be fitted in the model. It becomes messy very fast. So take out interactions fast if you can, if they aren't significant. So a lot of them have disappeared here. I've got a far simpler model in the next one here with fewer interactions. Yeah. P-values. No. Yep. Okay. Yeah. If all of them are significant. Yeah. But again, Yeah, good questions, because what you sometimes find is, for example, taking a look at, in this case, let's look at age here. Now, in this case, there's no significance at all. Suppose this one here was significant at age 20. Now, of course, because age is one variable, a factorial variable, factor with several levels, if any one of the levels is significant, the whole variable stays. I can't take out just one level of that, right, or two levels of that and keep the rest in, unless I split the thing into individual levels as particular variables. So I can have one variable for 19 which says yes, no, one for 20, and so on and so forth, but that's expanding the data quite a bit out. This is better because in the end I want to compare between the ages. So I can say, for example, here, if 20 is significant, then 20 is positive and the others are 0. I can say that age 20 has a high performance. Yeah, then they're the age groups. You're going to compare between the levels of the particular variable. So in this case, if any particular level of the variable, categorical variable, is significant, the whole variable needs to stay. Likewise with interactions, if any combination of interactions is significant, look at here, repeat, this is a good one here. Actually, yes. Repeat, no, this is different, doesn't work. Can't find one here straight away. Yeah, this one will work. I've got the year here as well as the group. So years versus groups, yeah. If any of these were significant, I have to keep the interaction term. Yeah, but there is a proviso here. Some judgment is involved. If one of these was significant, say, but the effect was small, if this coefficient was something like 0.0002, then that is my judgment and say the effect is so small it's not worth having the more complicated model with interaction term. Yeah, the effect is so small. So remember one thing we've said, probably I haven't said this in this class, that if something is statistically significant, it doesn't mean it's significant in the context. So you might find, if you look in medical data, something turns out to be significant in your model, but it's not clinically significant. Yeah, it's not important clinically. It's a very tiny effect. If I'm going to have a look at, say, two ways of doing something, two particular ways of running a business, for example, and one is better than the other one, but it's better and gives me an extra profit of $1,000 a year, it's not worth it to make all the differences and changes from this to that for the extra $1,000. So it's significant from the stats point of view, but not from the business point of view. So the context also determines significance in one sense. So if the effect here was tiny, although significant, I'd omit it, take it out altogether. And the same applies for main effects as well. So the thing with interactions is they make the model more complicated. You want to avoid them if you can. Yeah, but some interactions are important to know and understand. So the typical story is if I give plants water and I give them some fertilizer like nitrogen, then it's not just water or nitrogen that works. The combination works differently. Yeah, combination works differently. And that's what I'm interested in. How do they interact with each other? How much water do I require? How much nitrogen do I require together to give me the best production? That's important. But in this case, this is just observational data, not some experiment I've conducted. So I've got to be careful with the interactions. Try and avoid them if possible, is the idea. That's why when you fit models, you don't want too many interactions. And certainly, you don't want to go to interactions at the 3 level. You've got interactions between 3 variables. That's horrible to interpret. Very hard to interpret. In some cases, you might make some sense of it, but 2 is as high you really want to go, and not more than that. So yes, I did fit lots of interactions, but you'll find by the end my model comes out quite simple. And you might find I actually have dropped variables which look significant, but as I say, were tiny, or the interactions were there. But I might have said 4 levels of something and 3 levels of something else. There's one interaction somewhere that's significant, and to me that's not important to have the model as complex as that. And of course, you can compare models with ANOVA command or whatever else, or using AIC or whatever else to see if they're better or worse, and select that way as well to decide, well, I've got a term there that seems significant, but the effect is so small, it's not important. So yes, I've done a bit more here than I would normally, well, than you would be expected to do for modeling, meaning that you shouldn't have a model with too many strange terms. So you'll find that by the time I get to the end, a lot of things have disappeared. So I've done a full model thing here. I've shown everything that you could possibly do with the data as an example, illustration. But in general, yes, you avoid interaction. So lots of things I wouldn't, certainly things like this one here, you'll find will disappear very fast because there's nothing here at all to start off with. Now, having said that, as I said earlier, if you have two variables that align exactly, only one will be fitted in the model. It may be as I reduce my model, the other variable disappears, and then I can actually find this n is disappearing as well. And the other aspect is, we haven't seen this in this data, but sometimes you find a model you fitted here and everything is significant. Wonderful, but rubbish, because what you find if you look deeper excuse me, is that, as I've said this before here, you'll find the values over here are huge. They're very large indeed. Something's going wrong with the model. In a binary model, you have something like here, values for estimates of 10,000, 20,000, and the standard error also has 10, 20, 30,000 here. That's ridiculous. Something's going weird with the model and the way you fit it. Some variables have to be taken out of them because they're interfering with how the thing fits. And as you reduce the model, you'll find those things will disappear. And the way I do it usually myself is, if I've got this kind of model I'm fitting over here, and this isn't behaving itself, I'll just start off simple. I'll just take everything off and just keep one variable there. See if it behaves itself. Okay, fine. Add another one, add another one, add another one, until I add something that causes the problem. I know now where the problem is. Or, the other way, fit the whole thing in there and take out something. Take out something until you find the problem goes away. Then you know what's going on there. Is that good? Yes, Shane. In my case, I put the whole thing in there, but in your case, you might start off with a model that has few interaction terms, and start from there. And you can always, in the report, if you find nothing significant, there's two ways of handling that. In a short report like this, either you can say interaction terms weren't significant, nothing was found there, or just totally ignore it, say nothing. Either way is fine, right? Now, in some cases, I want to see that you actually tried interaction terms, and I can see that from your code into the report, right? In the larger article, you can have more space to write those kinds of things. But again, in the journal article of this kind, where you want to avoid technical stuff, you need to be non-technical as well, as clear as possible without being technical. Interactions are mainly understood, but don't get too technical with things. Any more questions? Yep. Well, what you've got here is log odds, right? When you take a look at the coefficients here. So if I look at, in the end, you'll find when I've got the final model, so this is my step IIC stuff just to see where it reduces to. So you can always use step IIC. The thing with the step IIC is, if you've got missing data, it doesn't work, because as the variables with missing data are dropped, the number of records changes, right? So step IIC assumes that the same data was used to fit all the models. So in this case, there's no problems. What you find when you've got problems with missing data, then it won't work. So this is just a quick way of getting to the model and then refitting the model to see what's going on. So this is, in the end, to work out the odds, well, you've got log odds ratio. To work out the odds, you take a look at the exponential of the coefficients. Yeah, that gives you the odds ratios. But again, the odds ratios have to be interpreted correctly in the context of the model you've got, and whether it's categorical or other variables. We know how tricky these kind of things can be. And the other thing is that, of course, you'll only report from here. This will give you the for the whole model, but you report here only the significant ones, especially with interaction terms. So not all the interactions will be significant. Only the significant interactions will be reported here. As you say, this one here is different from the other ones in this sense. For the O-rings one, this is well-known data. You've all seen this, and you'll find all reports and everything online as well. That's not so difficult. It's a matter of what you wrote down there more than anything else. And I was expecting to see at least one graph of this kind, so you can see what's going on there as far as the probability of, in this case, of breakdown was concerned, of the O-rings here. But other than that, not so difficult over here. And this one is similar. This is a single variable only, so very simple regression to fit straight away. No problems at all. Any more questions? Yes?
If you have a variable like a demographic thing like age being significant, do you have to talk about it in your report?
Yeah.
You just, like, you have to talk about the coefficient of everything, and then it's not a question.
Well, the thing is, you're looking at the effect of a particular variable. That's your interest, right? But the other ones are moderating variables. So like you're adjusting for the differences in other areas, and then you're saying, when after adjusting for all these, this is the effect of this particular variable. You should mention those, yes. It's a matter of how I mention the thing. Usually I tend to do the thing in the order of all the rubbish stuff first and get to the main thing in the end, saying this is the effect. Or you might sometimes cut the whole thing short, saying, adjusting for everything else, this is the thing we found with this variable, main thing. Everything else you can hide somewhere else. That's okay. The other thing with variables is, like age, for example, is a typical one. See, age, in especially student data, will be something like 17, loss of 17, loss of 18, loss of 19, loss of 20s maybe. In other words, there'll be quite a bit of data over here. And then it tails off, you get 25 somewhere, and you might get a 50 somewhere, and so on and so forth, right? A bit less data here. So while you want to make this categorical, not continuous, because you're saying essentially, if it's continuous, that means that means that as age increases, your effect increases linearly, which isn't the case. You're on different means for each of the ages separately. It's like saying, if I double my age, I double my performance. It doesn't work like that, right? So what you're going to do is actually have the thing as categorical. But the problem, of course, is because you've got lots more of this data and very few of this. And so what you need to do is draw a histogram of this data and see what it looks like. So I've got 17 over here, I've got 18 over here, 19 over here, 20 over here, and I've got 22, and I've got a couple over here. So then these categories are clear. There's quite a bit there. You might want to merge these rest together as one. Or maybe merge, or keep this separate here, and maybe merge these ones as one. So there's some decisions to be made here, some judgment to be used as well. You require care here, because depending on how you cut this variable into categories, your model will change its significances. Yeah? And so you can manipulate this. This is where you can actually lie with stats very easily, because you just manipulate the data in such a way that you get the result we want. Yeah? So be careful how you do this. There must be some clear reasons for doing it, especially things like this, where you've got clear demarcations between the categorical levels, where there are clear breakpoints as well. You can do that. And sometimes you find data looks actually, if you plot data especially, you might find it looks like this essentially. You might look at some scatter plot over here, and we've seen this in some other data here before. It actually, the scatter plot looks like it's in groups. I think we saw this with the abundance data with birds and things earlier. It looks like there are groups to start off with. So it's a matter of now saying, do I group this together here and make a categorical value out of this here? Or sometimes you might find that there are groups here, but there's sort of, this kind of thing happening here. Do I log it to put it back together again? So I'd first of all try the log thing, especially where the variable is clearly continuous, and try the log thing to see whether it works. If it doesn't work, then you can always categorize this into 3 or 4 categories if you wish. There's a lot of judgment involved, lots of experience here as well. Any more questions? Yep. For yes, you expect to do at least checking for the Poisson models for the dispersion, and seeing whether that behaves. And you should always look at also the regression, the plots of Pearson residuals, to see what that looks like it's behaving itself. Yeah, both of those. Yeah. The typical things for the thing is with Poisson and the non-continuous responses, you can probably do some scatter plots, but they mightn't be very informative. If I were to looking at the variables, categorical especially, and taking a look at tables of counts of Poisson with the categorical variables, scatter plots of the other ones, and histograms of data as well to see how it behaves, generally speaking. Yeah. Now with large data sets, this is quite tricky, because the thing with modeling is it's actually, people don't actually explore data very thoroughly to start off with, and they might look at the exploration of data and fit a model, and there's the end of it. The thing with data exploration and modeling is it goes together. You take a look at some data exploration, you fit the model, you see how the model behaves, You go back and look at the data to see where it's misbehaving, or maybe some interesting or different things or unusual things. You go back and look at the data again to see where those problem issues are, and try and redo the model if you can based on that information now. Yeah. And often, as I said earlier, you require to, once you've done the modeling, you might go back and see, can I do something with this variable, categorize it or scale it or whatever, as we've done before with transformations. That comes after the model's been fitted to start off with, right? You don't often make the decisions beforehand. You let the model do the talking for you and then decide based on the models what you'll do with the data next. So exploration, modeling go together. Don't separate them out. All good? All right, so for the exam, I'll be here next week. We will actually look at, as I was saying, the rest of the lecture notes. I don't want to go into details of those because it becomes rather mathematical. I'll leave it to you to look at over yourself. There's more information there, I think, than we need. Come next year, we might change the whole thing a little bit and change it quite a bit over there, I presume. But for the moment, we'll look at everything next week, this week 11. And I'll still be here in week 12 to answer any questions that deal with the exam. Of course, I can't answer questions directly on modeling and everything else, but if there's things or aspects, generally speaking, I can answer those. Yeah, so we'll do that as well next week. But I advise you to start early with the exam because while it's not difficult, I presume, well, I don't think it's difficult. Analysis will take you, if you understand what's happening in the analysis, you just bang it out. Poisson model, your quasi-Poisson, and the negative binomial. Done, straight away. Very easy to do those kinds of things. But then writing is the problem. The sooner you start writing, the more time you have to edit the thing yourself. And if you have the time to put the thing away for 2 days or so and come back to it, it'll be fantastic. It really makes the thing a little bit better. You know, it's a better difference of about 5 or 10 marks if you can actually edit properly yourself. Now, while I can be very fussy with my marking and reading as well, but I'll mark it fairly, of course. I'll mark the entire exam by myself. So my markers won't do it for me. It'll be maybe just marking the whole thing. So, but the thing is, if you have regular spelling mistakes, yeah, then that'll annoy me. Or if you have misreported things, if we've copied numbers incorrectly, that'll annoy me. Those kinds of things, yes.
So, you say Poisson and
Quasi and negative binomial.
Are we meant to track Poisson, check if it's
That's right.
and then if it's not, then go on?
Yeah.
Or do we do all three and then compare the three of them at the end?
Second part, I'll do both. I'll do the Poisson, and if it looks okay, you can say, well, that's fine. Well, I'll try the other ones as well to see what gives me benefit, especially with Pearson schedules. Then you can go back and report saying, we did Poisson, fantastic. We also tried these ones, and they weren't different. Yeah? Because if finding the model fits well, then the other ones won't make much of a difference. But sometimes you find Poisson looks great, lots of significances, but hey, the model is terrible because of dispersion or whatever else. So you need to go to the other models. Or sometimes they find Poisson just doesn't fit well. Lots of issues with the estimates. Either nothing significant, or the very large values of parameters or standard errors, or you have lots of significances. So you need to look at the model again and see, are the assumptions satisfied? Yeah? More often you'll find if the Poisson model doesn't fit, you won't have much in the way of significances. You change to the negative binomial, suddenly it works out nicely. Or you find everything significant in Poisson, you put negative binomial, things change quite a bit. Yeah? And as I said earlier, with this other problem with the inflated zero model, there's another model actually that's also interesting to talk about. So the two other ones are this zero inflated Poisson model, and the other one is the zero truncated Poisson model. So zero inflated has lots of zeros, and the truncated one is where there's no zeros at all. So for example, if you're looking at, say, the number of beetles on the leaves of trees, you only count those with beetles on them. A leaf, no beetles. You don't count that, right? You count the leaves with beetles on them. So there's no zeros in the data at all. So this is zero truncated Poisson model. And this will be adjusted as well, right? So all those are available in our online. Now, I'm hopeful and presuming that the first model you meet in real life won't be the zero truncated or the zero inflated. It will be the normal, beautiful, well-behaved Poisson model you can fit something to straight away. And then later, in 2 or 3 years' time, you understand this. Now you're getting something different, more complicated. You look at those things as you go along in life. Yeah. but maybe I'll consider whether I should put them, because the thing is, you won't see this again, Poisson models or these kinds of stuff, ever again in our courses over here. There's another aspect that I want to alert you to here, actually, while we're looking at this. The data we've got looking at for the exam and the way we're analyzing it is actually incorrect. But it's easy to do it that way. It's incorrect, not the right model for that. The reason is this. We are assuming that the data or the observations are independent, aren't we? And yet we have, for the same person, several different types of admissions or visits, health visits to the particular facilities. Those aren't independent, are they? The model's wrong to start off with. What we require is what we call a mixed effects generalized linear model, where you have some randomness built into the model. In other words, I need to take care of the random effect of the person itself, or if you like, I need to make sure I actually model the covariance between observations for the same person, the correlations. For the same person, the correlations that exist there, because they are independent, I have to model that as well separately, right? Now that's something you do in third year, next year. In fact, I'll teach that course myself next semester on the mixed linear effects models. But we'll do that for the normal models only. It also holds for the Poisson and other models as well. Yeah? So there's a different kind of model altogether where you have other problems. So even with the linear model, with the normal regression model, if you find your data isn't normal, what do you do? If you find your data actually doesn't have constant variance, what do you do? If you find your data is independent, what do you do? How do you deal with that? That's the next course. And so this is part of the same kind of stuff. But the thing is, since we haven't done that kind of model, this one still works fairly well for this kind of data here, right? So that's why we're using it. But yes, it doesn't, it's not the right model. In other words, if I was doing this properly, I wouldn't fit that model. I'd put something else. Yeah, and in fact, some of the data I'm looking at, in fact, along those lines, have those kind of model in there. It's actually quite complicated out there. The knee data, I'm not sure I mentioned this class, the knee data I'm looking at for one of the surgeons over there in Subiaco has exactly this problem here. He's got this complicated, it's a binary yes-no kind of idea, but you've also got this mixed effects model in there as well with binary. It becomes horrible. Yeah, but it has to be done properly, otherwise you're missing the whole point of the model. If you don't have the right model, your results mean nothing. It could be totally wrong. It could be actually dangerous. It could be the opposite. That's the problem here. All good? All right, we'll see you next week. I hope one more time, and then, as I say, I'll be here week 12. We'll decide what to do next week, actually, whether we actually hear week 12 or whether you come and see me in week 12 somewhere, meet somewhere else, or whatever. But I'd rather be here and see you all together than have 50 emails. Much easier. All right, thank you.